This work, entitled Stochastic Modeling and Analysis of the Energy Consumption of Wireless Sensor Networks, was submitted for evaluation to the IEEE Latin America Transactions journal with ID 7419. A wireless sensor network is an infrastructure formed by equipment for measuring, controlling, and communicating with a central station. The user can react to events related to the monitored phenomenon based on the information received. The wireless sensor network must have low consumption at the wireless nodes, with limited memory and processing capacity, and include communication systems, interface nodes, and application servers. Energy saving is still a challenge for wireless sensor networks to be popularized. Batteries need to be recharged or replaced, and energy collectors, despite increasing battery life, still have several challenges to be overcome. Several authors comment that energy efficiency is one of the most critical design factors for extending network life and reducing maintenance costs. Many studies provide interesting techniques for modeling and evaluating the power consumption of wireless sensor networks. It has been noticed, however, that an analysis that considers the probability distribution function, PDF, and the maximum and minimum expected values of the network's drained energy can complement those results. For example, the energy consumption values of different wireless sensor networks can have the same mean but different probability distribution shapes. An approach to model energy consumption is proposed based on the fact that the energy consumed per cycle by any sensor node of the network is a random variable. In this work, one possible formulation is presented, considering that the devices are configured so that the consumption of all states tends to the minimum limit, forming a well-designed WSN. In addition to the PDF, maximum and minimum power consumption probability distributions establish theoretical power consumption limits and give more information about the most probable range of energy values. This is accomplished by calculating the expected values of the maximum and minimum PDFs. LoRaWAN is a free and open-source simulator developed in MATLAB to evaluate the behavior of the medium access and physical layer of LoRaWAN networks. We established 6 scenarios to analyze the effects of the transmission period, the environment, and the number of gateways. In all scenarios, 200 end devices were placed randomly in a circular area with a 4 km radius. Regarding the transmission period effect, 2 scenarios have been evaluated. In both cases, the end devices exchange data with a single gateway in a free space environment for 30 seconds and 300 seconds transmission period. As was to be predicted, transmission interval lengthening results in reduced power consumption. In the case of period equals 300, simulation results more closely match the theoretical PDF. Energy consumption observations for the period equals 30 scenario are slightly above the convolution of exponentials probability distribution. Greater concurrence for the medium explains this by high interference and collisions, pushing energy consumption numbers further from the minimum. The end devices communicate with a single gateway in a free space environment and inside a space with obstacles. Deploying the nodes in a hasher region has the expected effect of increasing energy use. The theoretical PDF is more closely matched by the simulation findings for the free space scenario. The observed energy consumption for the obstacles scenario is slightly higher due to smaller signal-to-noise ratio. So the LoRaWAN ADR algorithm increases the transmission power of the nodes. In these 2 scenarios, the nodes are distributed for communication with both 1 and 15 gateways placed randomly. The objective is to evaluate the model with intense medium concurrence and lower signal-to-noise ratio. The simulation results align with the theoretical PDF when 15 gateways are functioning, as expected. The uplink delivery rate decreases as the power consumption increases when the period equals 30 and 1 gateway is used. It is possible to notice that the verified minimum and maximum collected from the simulation are different from the expected minimum and maximum. This is to be expected since the ADR algorithm can optimize the network in such a way that the energy consumption of most nodes is closer to the minimum. Some outliers were detected, as can be verified by comparing the expected maximum for t equals 300 and n equals 4 case to the verified maximum. The energy consumption and the uplink delivery rate improve as a result of more gateways. For the analyzed scenarios, the energy consumption of all network nodes are between expected maximum and minimum theoretical prediction except for scenario 5. In addition, it is possible to conclude that scenarios 3 and 4 are better designed than scenarios 1, 2, and 5. The main contribution of the paper is the developed approach which can be used to evaluate WSNs with more detail. Based on the results, the authors expect WSN designers to have more subsidies to examine the performance of different applications in this area of knowledge using the proposed methodology. Other probability distributions can be used to model the power consumption depending on the random dominant mechanism and will be investigated in a future work. Thank you for watching.